The value of standard deviation can also be used in combination with the mean value of a dataset, along with the use of normal distribution curves to represent the dataset. This because normal distribution curves can be multiple different shapes with varying heights and widths to the curve, and this shape of the distribution curve represents the values for both the mean and the standard deviation of a dataset. For example, as seen in figure 22 with the distribution curve labelled small standard deviation, the curve is narrow, which means that the data points are all close to the mean value, which therefore means that the standard deviation is small, because the data values differ a very small amount from the mean value. This then means that the mean is able to be considered more representative of the data set, as all the data values are close to this value. However, if the curve looks like the curve labelled large standard deviation in figure 22, it means that the spread of the data is larger, so all of the different data points differ a large amount from the mean, meaning that the standard deviation will be a large amount, and also means that the mean value is less representative of the data set. Decision. However, when deciding on what value to use to represent the data, the researcher must choose depending on what one of the values is most appropriate to be used for the type of data the researcher has. This value could therefore be either a central tendency value or a dispersion value. For example, the mean and standard deviation are both most appropriate to be used when the data is either integral ratio rather than nominal or ordinal, whereas the median range and interquartile range can be used when the data is either ordinal, interval, or ratio, and finally the mode is appropriate to be used for all four of these types of data, these being nominal, ordinal, interval, and ratio. Inferential statistics. Inferential statistics used to give more meaning to the data collected, as it gives further data to the researcher and can show multiple different factors and emerging themes from the data, such as whether there is a relationship between the data and any differences in the data. When deciding the appropriate test to use to analyse the dataset, the researcher must follow through with a decision tree, as this will make the researcher answer questions about the dataset until the tree eventually leads to a specific test that should be used. These questions are things such as what type of data the dataset collected is, such as whether it's nominal or ordinal, and whether the dataset collected is two related groups of data or two separate groups of data, as these questions means that the researcher has to follow the branch with the answer that applies to the data until they eventually reach the data test that should be used on their data. Furthermore, there are always two stages to statistical analysis tests, with the first stages being different depending on whether the statistical test being used is testing for a relationship or difference. When looking for a difference, the first level of analysis is to search for a mean difference, and the second level would be to determine whether this difference is statistically significant or not by comparing the results gathered in the first stage to the p-value. Whereas if the statistical test is looking for a relationship, then the first level of analysis is to find the r-value, which is the correlation coefficient, and therefore the value which shows the strength and direction of the correlation. This correlation coefficient is between the values +1 and -1, and if the value is negative, then it shows a negative correlation, and the positive value shows a positive correlation. Furthermore, the closer to the +1 and -1 the correlation coefficient value shows, the stronger the correlation. The second level of analysis is then comparing this value to the p-value again to determine whether the correlation is statistically significant or not. The statistical significance stage is when the value collected during the first level of analysis is compared to the level of significance or p-value to test whether the correlation/difference is significant. This p-value is typically set up to p is less than 0.05, which means that if the value is below 0.05, then there is a significant outcome, this outcome being either the difference or correlation, and if the value is equal to 0.05 or larger than 0.05, there is no significant outcome. However, looking solely at the statistical significance of a difference or correlation is not always appropriate, and sometimes it is better to look at the physical significance. This is because the physical significance is more relevant to real life, such as running times in a 100-meter sprint, as if the runner did two sprints with one being before and one being after 6 weeks of training, there's a difference of 0.12 seconds between the scores in favour of the sprint after the training that may not be statistically significant. However, it is extremely significant physically, as that time could be the difference between winning a race or not. Difference. When looking at differences, we are testing the null hypothesis, as the null states that there will be no significant change. However, by doing the statistical test to test a change, we're looking for any significant changes, and so we're testing for whether the null is correct or not. There are many different tests that could be used to test for differences, and so to be able to pick a specific test to use, the researcher must use a decision tree to help them. This is used by answering a series of questions about the data that the researcher has until it leads to the test that should be used, such as in the example in figure 30, where the first question is how many samples the researcher has, which then leads to further questions such as the type of data the data sets is, nominal, ordinal, etc., and this leads to how the test that should be used. Once the statistical tests have been completed, the researcher will get a t-value that must be compared to a critical value to work out whether the difference is statistically significant or not. This is done by following one column down for the level of significance that is being used. In most cases, this is p is less than 0.05, and one row across for the equivalent DF value, which is different depending on the test you could do, and normally equates to a formula based on the number of participants used, such as the number of participants used minus 2 equals the DF value. Once these two then meet on a number, this number is the critical value, and if the critical value is larger than the t value, then the difference is not significant, but if it is smaller, then there is a significant difference. Dependent t-test. Once the dependent t-test has been completed, it will leave the researcher with a t-value that is representative of the difference between the datasets. This t-value must then be compared to a critical value, found through the use of a critical value table, in order to see the difference was significant or not. The formula that is used for the dependent t-test can be seen in figure 31, where the top line is equal to the sum of all the differences between scores. This is then divided by the square root of the number of paired scores multiplied by the sum of all difference squared values, take away the sum of all difference values squared, and divided by number of paired scores minus 1. In figure 33, it shows a worked example of a dependent t-test, where the values from the data table shown in figure 32. The values that are being compared to are from the two tests for speed, the static sprint and the flying sprint. The first stage to working out the t-value in this test is to input the values, which becomes minus 1.31 for the sum of all the differences, 6 for the number of paired scores, 6.0345 for the sum of all different squared values, minus 1.31 for the sum of all differences, and 6 for the number of paired scores. From here, all the stages are to do with simplifying the equation until it gets to a stage where it is easy to do. The division to find the t-value, which in this case was when the values were 1.31 divided by 2.626348653, which gave a value of minus 0.498774216. Independent t-test. The independent t-test gives a t-value, same as the dependent t-test. However, this time the test is looking at the mean and standard deviations of the two sets of data values. The formula that is used to complete this test can be seen in figure 34, where the M1 and M2 values are equal to the mean values of dataset 1 and 2, and this then divided by the square root of the standard deviation of dataset 1, squared divided by the number of participants in group 1, plus the standard deviation of group 2 squared divided by the number of participants in group 2. This will then give a t-value that should be compared to a critical value to determine whether the difference is statistically significant or not. In figure 36, there is a worked example for an independent t-test, where the data values have been taken from the data table shown in figure 35, where the data has been taken from that collected during the set and reach tests for group A and group B. The first stage shown in figure 36 is to input the data values into the formula, which becomes 35.4286 take away 33.174 divided by the square root of 8.6189 squared over 7 plus 11 squared over 7. From this stage, the next few levels are to simplify the equation until it gets to a stage in which the division to find the t-value is done easily, which in this case is when the equation is 2.2546 divided by 42818481235264661. This gives a t-value of 0.416858165541, which should then be compared to the relevant critical value taken from the critical value table to see whether the difference between the datasets is statistically significant or not. However, there are not only two tests that can be used for the test of difference between datasets. There are multiple others that can be used. For example, the Wilcoxon matched pairs signed ranks test, the Mann-Whitney-U, and the chi-square test. The reason there are multiple different tests to test for the difference between datasets is due to there being different sets of criteria that each test fills, and so each test tests on a different type of dataset, as it is more relevant to be used for specific datasets to give a more accurate test, such as if the test is ordinal data, then a different test would be used than if it was nominal data. Relationship. However, instead of wanting to search and test for differences in the datasets that the researchers collected, they may decide that they want to test for a correlation between the datasets. A correlation is a value for the level of relationship between two or more variables. This value is between 1 and minus 1. The closer to 0 the value is, means the weaker the correlation, but the closer to 1 or minus 1 it is, means the stronger the correlation. Alongside this, if the value is negative, it means there is a negative correlation, and if it's positive, then there is a positive correlation. To determine the test that should be used to analyse the dataset the researcher has, they should use a decision tree to help them. It's because the decision tree will make the researcher answer questions based around the data, and these answers will then lead to the test that should be used to analyse the data. For example, as can be seen in figure 23, the first question will be asking what type of outcome the researcher is looking to gain from the test, whether this is correlation or a difference. In this case, the answer would be correlation. The second question is then asking what type of data the set it is, whether it's parametric or non-parametric, and both of these would then lead to two different tests, with parametric leading to the Pearson correlation, and non-parametric leading to the Spearman rank order. Pearson correlation. If a researcher has previously made an assumption that the two datasets they are looking at are normally distributed, then the Pearson test is used and will give a value for the correlation coefficient between the two sets at the end of the formula. Once a test has been completed, it gives an answer for the correlation coefficient, which is a number between +1 and -1. The closer to 0 this number is means the weaker the relationship, and the closer to +1 and -1 means the stronger. However, if the value is a positive number, it means there is a positive correlation between the two datasets. If the value is negative, then there's a negative correlation. The formula for this test is shown in figure 24 and means that R value, correlation coefficient, is equal to the number of participants multiplied by the sum of scores for the x and y values when they have been multiplied together. Take away the sum of all the x values and sum of all the y values multiplied together. This is then divided by the square root of the number of participants multiplied by the sum of all the x squared values. Take away the sum of the x values squared, and this is then multiplied by the same stages but for the y value. In figure 25, it shows a worked example of how to calculate the R value by using the Pearson correlation test. The data that was used during this example can be seen in figure 26, where the x values have been taken from the skin fold calipers scores for biceps and the y values for triceps. The first part of the worked example was to input the numbers into the formula and to simplify, which became 3.3448 for the number of participants multiplied by the sum of the y values, 58 for the sum of the x values, and 55 for y. 892 for the number of participants multiplied by the sum of all the x squared values to take away the sum of the x values squared, and finally 327 for the same system but for the y values. The next stage was to simplify each time until we came to an easy point to divide one number by another to give an R value. In this case, the stages lead to the point where we could divide 258 by 440.0777772177, which gave us an R value of 0.47770897. This R value shows there is a positive correlation between the triceps and biceps scores in the skin fold calipers test, but it's a fairly weak as it is closer to 0 than it is to 1. Spearman rank correlation test. The Spearman test is used when it has not been assumed previously that the two datasets are normally distributed. However, it gives the same value as the Pearson test. It gives a correlation coefficient R value. The formula that is used for the Spearman test can be seen in figure 27, which shows that the R value is worked out by taking 6 multiplied by the sum of all the d squared values, divided by the number of participants multiplied by the number of participants squared, take 1. And the answer to this is then taken away from 1 to give the correlation coefficient. In figure 29, we can see a worked example for the Spearman test, where the data values have been taken from the data table shown in figure 28, where the values are from 2 tests. Tests in which the data were originally collected from are now being compared to the standing vertical jump and fire girth. The first stage was to input the values into the formula, which became 118 for the sum of all the d squared values, 10 for the number of participants, and 100 for the number of participants squared. From this stage, the following ones are all used to simplify the equation until it gets to a point where the division to get the number that will be taken from 1 can easily be done. In this example, it took only 3 more stages until this point, where the numbers became 708 divided by 990, which equals to 0.71515152. Therefore, the next stage is to take this number away from 1, and this will give us our correlation coefficient, which in this case becomes 0.2848 reoccurring. This shows that there is a very weak positive correlation between standing vertical jump scores and fire girth. However, there's also one more test that can be used instead of either the Pearson or the Spearman test, this test being the linear regression test, which is only used when there is one independent variable and one dependent variable, where the independent causes a change in the dependent variable. While these tests can be done manually, in most cases the researcher will use Edexcel to do the calculation for the test. This is because it not only takes less time, as the values just have to be input into the calculation rather than going through all the stages of the calculation. Furthermore, doing the calculations for the use of a system such as Edexcel mean that the answers that are received won't be a chance of error during the working out, whereas if the calculations were done manually, then the likelihood of getting an error in the results are much higher. Reference list.